Today I'm going to show you two different ways to do electron configurations. And basically, if you understand orbital diagrams from yesterday, you'll understand these two ways because basically they're just shorter versions of the orbital diagrams. So before we begin, you're going to need out your periodic table and your notes sheet. So make sure you have both of those things out. And as we go through this video, if at any point you need to pause the video to do an example or to do some practice, definitely pause it and then resume the video as needed to check your work. All right, so we're going to start with SPDF notation, and I want to show you what this notation would look like for chlorine. So we know yesterday we did the boxes and the arrows for the orbital diagram with the numbers underneath. Well, today we're going to see what SPDF notation would look like, and it's going to look familiar. So this is what the electron configuration for chlorine would look like using SPDF notation. If you notice, it basically looks like what we did yesterday. The only difference is it's just the letters and the numbers that were below the boxes. So we don't have to do the boxes, we don't have to do the arrows for SPDF notation, but you still show the numbers and the letters that you were writing below. So this is definitely much quicker. And for those of you that can trace this on the periodic table, you'll be able to quickly do this, and it should save you a little bit of work because you won't have to do the boxes and the arrows. So what we're looking at here in purple, the large numbers, they represent which energy level you're in. Remember, we can get the energy level from the rows on the periodic table, and they're always the big numbers in front. The letters represent the sublevel, so S, P, D, or F, and the green superscript numbers, they represent the number of electrons in every sublevel. And remember, you can use the periodic table here to guide you as you do any of these. Okay, so if you can trace this on the periodic table, you can do SPDF notation for any element. And again, it's just a simpler version of orbital diagrams. You don't have to use the boxes and the arrows. So if you need to pause here, you can pause so you can fill out your note sheet, but then continue when you're done with that. Okay, so a little bit of review from yesterday. We learned yesterday that the periods or the rows indicate the energy level that you're in. So these numbers here that are going down the left side of the periodic table, those are telling you what energy level you're in. However, if you remember from yesterday, we said that the D sublevels are off by 1. So even though right here we have our D sublevel starting for the first time, even though you're in the 4th row, you're not in the 4D, you're in the 3D. And then when you're in the 5th row, you're not in the 5D, you're in the 4D, and so on. All right, so we didn't necessarily talk about why this happens. So now we need to just briefly talk about this. So the easiest explanation of why this happens is that we talked about yesterday the off-bow principle. The off-bow principle says you fill the lowest energy levels first. Okay, so if it's lower in energy, it gets filled first. So this D sublevel is so large, it has 5 orbitals, so it actually has a little bit more energy than the S that comes before it. So this 4S here is a little bit lower in energy. It's smaller, okay? So it comes first or fills first, and then the D sublevel comes after that because it's a little bit higher in energy. So off-bow says fill the lowest energy first. So if the 4S or the 5S, so on, is a little bit lower in energy, they fill first, and then the D sublevel from the previous energy level fills. Okay, so this is just something you have to remember, that even though you're in the 4th energy level or the 4th row, you're 1 behind for the D. You're in the 3D, okay, and so on. We also talked about yesterday how you could see the sublevels on the periodic table. So we know that the groups here, the columns, are going to be similar sublevels. So we know over here on the left, The first two groups, first two columns are going to be your S sublevel. Remember, helium over here, he's also included as part of the S. Your P block is over here on the right, the group of 6. The D block's in the middle, and the F's are down below. So those are your sublevels on the periodic table, and you need to know where they're at. You need to be able to look at a periodic table and know where the S, P, D, and F are located. All right, so if you need to pause now, pause, and then move on to the next slide. So this is just showing you the energy level and sublevel that would be associated with each element or each area on the periodic table. So if you're having trouble, doing these electron configurations, this basically traces the periodic table for you. Okay, so you start up here with hydrogen. This is your 1s. Then as you go over to helium, you're still in the 1s. But then you wrap down here to the 2s. Keep going, you get to the 2p, then the 3s, the 3p, 4s, and then your 3d start, and so on. So this is a really good picture if you're struggling here to trace this. But again, all this information can be pretty much found right on your periodic table. The big number represents which energy level or row you're in, and the letter is the sublevel, which we just went over about how to find where they're at. All right, the only thing you need to remember is that the D sublevel is one energy level off. So this picture is showing you the last electron for every single element on the table. Okay, so if you pick a particular element, you can see the exact last electron here. So if we're looking at chlorine here, which we did earlier, all right, the very last set of electrons here that's filling would be the 3p5. So chlorine would be, the 1s2, 2s2, 2p6, 3s2, 3p5 would be its last electrons. So you can see that there for all the elements on the table. Okay, so now we're going to try an example. I want you to write the electron configuration for boron using this SPDF notation. So you don't need any boxes, any arrows. We're not doing an orbital diagram. Just do this using the SPDF notation. So pause the video and then resume it when you want to see if you're getting this right and how to go about doing it. All right, so now I'm going to show you how to write the SPDF configuration here for boron. All right, so you find boron on the periodic table. Boron is right here, number 5, so we're not going to have to go that far. All right, we only have 5 electrons essentially to show. So you always start at the periodic table at the top with hydrogen and trace your way along using the energy levels and sublevels until you get to boron. Okay, so the first thing we see here, if we're starting at the top, we're starting with hydrogen. All right, you got to think about what energy level and what sublevel are you in. Okay, so if we're at hydrogen, we're in the 1s sublevel. We're in the first row, so that's the 1, and we're in the S sublevel, and you can see that labeled on your table. All right, but if we fill this, we're not going to be at boron, so it's going to be 1s2. Okay, that'll take us through hydrogen and helium. And after element number 2, okay, comes element number 3. So we're going to be down here. All right, so again, think about it. What energy level? What sublevel are you in? All right, so now you're in the second energy level. You're still in the S, and it's going to be filled, 2s2. All right, so the 2s2 takes care of these 2 elements, okay, lithium and beryllium. And right now you have a total of 4 electrons shown in your configuration. So after element number 4 comes element number 5. So we're at boron, okay? So we're still in the second energy level, so it's 2, but now you're in the P, okay? But there's only 1 electron left to reach boron. So even though the P can hold 6, it's just 2p1, okay? If you add up the superscript numbers here, 2, 2, and 1, it gives you a total of 5. And that is the number of electrons for boron. So you know that you did this right. So that would be the electron configuration of boron in SPDF notation. 1s2, 2s2, 2p1, and you don't have to show any boxes or arrows for the SPDF notation. All right, so now we're going to try some more examples here. I want you to write me the electron configurations for these 4 elements: helium, neon, sulfur, and strontium, using the SPDF notation. So take a few minutes here, do this. Don't forget to answer this last question. How many electrons are there in the last energy level for each? Okay, so you can take a few minutes here, do this, pause the video, and then when you're ready to see how you did, resume. All right, so let's do these electron configurations here real quick. So again, you have to start at the top of your periodic table with element number 1, hydrogen, and then just keep tracing along, increasing your number slowly until you get to the element you're looking for. And you have to include any energy levels and sublevels you pass along the way. So if we do this for helium, all right, helium is number 2 on the periodic table. We start with hydrogen and work our way. We're going to start in the 1s, and there's going to be 2 of them. All right, and that takes us to element number 2, helium. You can check yourself here because, the superscript number 2 tells you how many electrons you have. You have 2, and that's how many helium has. Okay, so if we continue now and do this for neon, all right, neon is element number 10, so you're going to have to go a little bit further here, but it's the same idea. Just trace your way until you get to element number 10. So we'll do 1s2, 2s2, 2p6. Okay, if you total up your superscript numbers, they're going to add up to 10. You have reached neon. Next one was sulfur. All right, sulfur is element number 16. So we got 1s2, 2s2, 2p6. That takes us through element number 10, but we still have to keep going. We still have 6 more electrons. So now we'd be in the 3s2 and then 3p, but there's only 4 electrons left to get to sulfur. All right, even though p can hold 6, we don't write 3p6 because that would take us up through element number 18. And sulfur is number 16. You can only have 4 in the 3p. Okay, so the last example we're doing here is strontium. Strontium is a little bit further down the table here. It's element number 38. All right, so we're going to have to go a little bit further. So we have 1s2, 2s2, 2p6, 3s2, and this time we will have 3p6. That'll take us up through element number 18, but you got to keep going here. So next is the 4s2, then 3d10. Remember, the D sublevel is 1 off, so even though you're in the 4th row, you're in the 3D, but then you're back to the 4p6. All right, that takes you up through element number 36, so you still have 2 more to go to get the strontium. That's going to be your 5s2. Okay, so that takes care of the electron configurations for each of them, but then we still have this last question about how many electrons are in the last energy level here for each. So if we do this for helium, the last energy level is its only energy level. It has a 1s. So the last energy level or highest energy level for helium here is the 1, and he only has 2 electrons. Okay, but now if we do this for neon, all right, a lot of people will say that the electrons in the last energy level for neon are 6. However, you need to realize that the last or the highest energy level for neon is 2. The energy level is written in front. The big number in front is the energy level. So neon has electrons in the 2s and the 2p. So these 2s electrons count towards the total number of electrons in the last or highest energy level. So neon has 8 electrons, okay, in the highest or last energy level. So you have to be careful of that. All right, any electrons that are in the highest energy level need to be taken into account here when you're doing this. So if you look at this now for sulfur, the highest or last energy level for sulfur is the 3. That's the highest energy level it has. So these 2 and these 4 are going to be in the last energy level. So it would have 6 total in the highest or last energy level for sulfur. And then last but not least here for strontium, right, the last energy level is 5, and it only has those 2 electrons. So just be careful that that's something to watch out for when you're doing this. So now you should be able to do electron configurations in SPDF notation. So now that you've learned orbital diagrams and SPDF notation for electron configurations, I'm going to show you an even shorter way to do this. It's called kernel notation or shorthand notation or noble gas notation. It's an even shorter version of SPDF. Now, you're only allowed to do this if it explicitly asks you to do the kernel or the shorthand notation. Okay, so you wouldn't do this all the time, but it's another way to do this here. So if you look here, how you do this is you would write the symbol of the noble gas that precedes the element that you're doing here, right? Precedes means the noble gas that comes before the element you're doing. Just like the preseason comes before the season, okay? If something precedes something, it comes before it. So we didn't talk about where the noble gases are yet on the table. This is next unit. So I left you a note here that this is the farthest right column on your periodic table. So if you look at your periodic table, it's the column that goes from helium on down. All right, so helium, neon, argon, krypton, xenon, radon, so on. Okay, those are your noble gases. So you put the symbol of the noble gas that comes before the element you're doing in brackets. Okay, then the next thing you do is you write the remaining electrons that are left for the element in SPDF notation. Okay, so for example here, if you were writing out the SPDF notation for aluminum, right, this is what you would write out. Okay, 1s2, 2s2, 2p6, 3s2, 3p1. If I allowed you to do this in this shorthand notation, okay, if you find the noble gas that comes before aluminum, all right, it would be neon. All right, aluminum is number 13. Okay, the noble gas that comes after aluminum would be argon, number 18. So the noble gas that comes before him is neon. All right, so if you look at the electron configuration of neon right here, it'd be 1s2, 2s2, 2p6. So by putting the neon in brackets, okay, by doing this, basically it allows you to say, okay, I don't have to write any of neon's electron configuration. You get to kind of wipe it out. It's basically like saying, okay, I'm good through element number 10. So then you just have to write what's left of the electron configuration until you reach the element you're doing. So by putting neon in brackets for aluminum, okay, is basically like saying, okay, I get to start at element number 11 and then continue until you reach aluminum. So then if you're at element number 11, where are you at? You're at 3s2 and then 3p1, okay, and then that will get you to aluminum. Okay, so you put the noble gas that comes before it in brackets, and then you basically start with the element that comes after it and trace your way along until you reach the element that you're doing. If you check here with the number of electrons, neon has 10 electrons, plus 2 is 12, plus 1 is 13. Aluminum has 13 electrons, so you know you did this right. So right now, I want you to try to do this shorthand notation for calcium and antimony. All right, and then once you do it, resume the video and see if you did these correctly. Okay, so let's see how we did here with this kernel or shorthand notation for calcium, Ca, and antimony, SB. All right, so in order to do this, you need to find the element on the periodic table. So if you find calcium on the periodic table, it's number 20. You're looking for the noble gas that comes before calcium. So that far right column, the element that comes before calcium. All right, so the noble gas that comes before calcium is argon, number 18. So you put the argon, Ar, in brackets, and basically what that means is you're good through element number 18. So you get to start at number 19, and you just keep writing SPDF notation until you get to calcium. So all that's left here then is 4s2. okay? If you want to see if you're right, argon has 18 electrons, plus the 2 from the 4s gives you 20, which is the total number of electrons for calcium here, okay? So if we're going to do this now for antimony, antimony is number 51, so the noble gas that comes before antimony is krypton. So you put the krypton in brackets, and then basically what that means is you're good through element number 36. You get to start at element number 37. All right. So if you look on your table, element number 37 is in the 5s. So you have 5s2. Okay. And if you keep tracing, now you're going to be in the 4d 10. Remember, D is one energy level behind. So even though you're in the 5th row, you're in the 4D. All right. And then you have to do what's left until you get to antimony. So you're back in the 5, but it's the 5p. And then you have 3, okay, 3 electrons here until you get to antimony. So you can see here that this is definitely a shorter version to do the electron configuration. It's way shorter than orbital diagram, a little shorter than SPDF. But again, you really are only allowed to do this when it explicitly says do the kernel or shorthand notation. Okay, so we have one more thing to look at here. As with anything great, there's always exceptions, okay? And there's actually a lot more exceptions to these rules than you would think, but we only really look at 2 specific examples here. So there are times when the electron configurations might be different from what you would expect according to the rules here. And a simple explanation of why this happens, and this is not necessarily the exact reason or an AP level reason, but just to keep it simple for you, the basic gist why this happens is that sometimes these half-filled or fully filled sublevels are a little bit more stable, okay? Or they cause less repulsions here with the electrons. So these exceptions kind of happen for that stability, all right? So the easiest examples we can look at are chromium and copper on your periodic table, okay? So if you look here, all right, look for chromium on your periodic table. It's number 24, all right? What you would expect to happen here is you would expect chromium to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, okay, 3d4. That's what you would expect chromium to be. However, this is not what chromium does for its electron configuration, okay? What it does is it actually borrows one from the 4s and puts it in the 3D, okay? So this is not right, okay? This is what it actually ends up doing, all right? It borrows one from the 4s and puts it in the 3D. So it becomes 4s1, 3d5, okay? So yes, that is definitely something that you would not expect. You would not expect the D sublevel to be filling before the 4s is completely filled, but that's what it does, okay? So this is just something you have to watch out for. Notice what we did not do. I didn't add an electron. If you total up the number of electrons here, total up those superscript numbers, it's still going to be 24 total electrons, okay? You just moved one, all right? If you made it 25 electrons, that would not be chromium anymore. That would be manganese. So it still has to have the same number of electrons. It just moved one, all right? So now you would expect the same thing to happen with copper, but a little bit different. So I want you to try the electron configuration for copper on your own, and then resume the video and see if you got this. And I can show you a little bit more detailed explanation using orbital diagrams about why this happens as well. All right, so I just want to look at this a little bit more. I'm still going to stay on chromium for a second. All right, what we would usually expect here, okay, for chromium, if we were doing an orbital diagram, because the orbital diagram kind of helps you see this a little bit better, you would expect to see a 4s, and then you would have your 3D. Okay, remember Ds have the 5 orbitals. Okay, so you have your 5 boxes there. What you would expect here for the chromium is you would expect to be 4s2 and then 3d4. Okay, that's what you'd expect from the rules. But notice, okay, there's something to take note of. Do you see how in the 3D, the first 4 orbitals have 1 electron each, and this last one is missing 1? All right, so the easiest explanation here is if this last box also had 1, that 3D would be half filled, where it would have 1 electron in every single orbital. Okay, so in order to minimize these repulsions here, basically what happens is chromium will move one of its electrons here. Okay, so it's not adding an electron, it's moving an electron. All right, so this electron here goes away. All right, so we're going to rewrite this here, and these change as well. So when we redo this, all right, it takes 1 from the 4s and puts it in the 3d. So this becomes 4s1, 3d5. And if you notice, okay, now every single one of these orbitals has 1 electron in it, all right? And because of the minimization of the repulsions, this is more stable for chromium. So anytime you see chromium, you have to remember, no matter which configuration you're doing, it has to be 4s1, 3d5, and that's just something you need to know, all right? So now, if we look at this for copper, it's going to be a little different, but same idea. So copper is number 29 on the periodic table. So he would be in the 4s as well. All right. And he also has the 3d. All right. What you would expect here for copper is you would expect 4s2, 3d9. All right. If you were following the rules, that's what you would expect. Okay. Do you see how this last orbital just needs 1 more electron to make that 3D completely filled? All right. So in order to make this more stable, in order to minimize the repulsions, copper will literally move 1 electron from the 4s to the 3D. He's not adding an electron, he's moving 1. Okay. So we'll get rid of this, make the change here. All right, so for copper, he's actually going to be 4s1, 3d10. All right, now that 3d sublevel is completely filled, but there's only 1 in the 4s. You have to remember that anytime you see copper, any configuration, this is what you would expect to see. 4s1, 3d10. Everything before this, all right, is the same, except you get 4s1, 3d10. Don't start doing this for electrons, for all these different elements. No, we only need to worry about these exceptions for chromium and copper. What happens is people start moving electrons around for other elements in different places on the periodic table, but it's only these 2 elements. So this is just something you have to know. So now you should be good with SPDF notation and the kernel or the shorthand notation.